Hi, everyone. So I would like to share some ideas from two papers. Both are joint work with Noam Nissan. And in these papers, we study scenarios in which we have several strategic users that interact in some platform. And these users are assisted by automated learning agents. And the agents play the game on behalf of the users and aim to optimize for them. This is motivated by many scenarios in which we would like to have automated tools that will work for us, but these automated tools, in fact, live in complex environments where they need to interact with other automated tools that work for other users, possibly optimizing different objectives. And first example we're going to look at are online auctions, similar to those used by the large internet companies to sell ad positions online. And so we know that those are very big markets, and these auctions typically run at extremely fast rates, and bids are not being placed directly by the users. Instead, they're being placed by various types of automated bidding tools. And the way this auto bidding basically works is that users enter some of their private parameters into the auto bidding agent interface. Parameters can be the value that they have for the item that's being auctioned, or their budget, or other parameters. And then these agents automatically place bids in some long sequence of auctions, interact between themselves, and learn over time. And the users can observe the long-term outcomes from this long sequence of auctions. And a long sequence, again, can be a few minutes, a day, a week, and so on. So to illustrate this, let's first look at the classic auction setting. So this is without automated bidding. Here we have two players, Alice and Bob. Each one of them is going to enter a bid, place a bid in the auction. The auction is going to determine the allocation and payment. And Alice and Bob are going to get some utility from this allocation and payment, and this should go on repeatedly. Now, the automated bidding setting is a bit different. So here, Alice and Bob are going to enter some of their private parameters into the auto bidding agent interface. And we're going to focus on the value that they have for the item in the auction as the parameter. Then these bidding agents are going to place bids in a sequence of auctions, and Alice and Bob can observe the long-term outcomes and get some utility from these outcomes. What's actually going on in this gray box here is that every bidding agent is running some learning algorithm aiming to optimize utility for its user. But importantly, it's optimizing according to the parameters that were entered by the user. So you can notice that the auction that Alice and Bob, our users here, actually observe and play is not exactly the same as the underlying auction that runs inside the platform. Instead, they experience what we call a meta auction, in which their action spaces are the possible parameters that they can give to their bidding agents. And their utilities are determined according to long-term outcomes of the dynamic between those learning agents. And in the second paper, we define and study these metagames in a general context, and we see interesting results that arise in various types of settings. So I'll get back to that more in the end. The types of learning agents we're going to look at are agents that achieve what's called no-regret learning outcomes. In particular, we're going to talk about external regret, meaning that agents play such that the long-term average empirical payoffs approach the payoffs of the best fixed strategy in hindsight. There are many well-known examples for algorithms that have this no-regret property. And importantly, there is empirical evidence that real-world bids in these ad auctions are by large consistent with the regret minimization model. And we know that no-regret dynamics approach the set of the course-correlated equilibria of the game. In fact, this is by definition, if all the agents have low regret, then the empirical distribution of play is close to a course equilibrium. But we also know that in many games, including our auctions, the sets of course equilibria may be quite broad, and different course equilibria can give different utilities for the players. And recall that our motivation here is that we would like to be able to say something about the incentives of our users in this system that includes automated agents. And for this, because different course equilibria can give different outcomes, we will need to analyze convergence of the dynamics and understand what's actually going on in these auctions with automated bidding. Let me just very briefly recap. So we talked about those meta auctions, which we have users that enter parameters into a bidding agent, and then those bidding agents interact, and the dynamic induces some incentives for some utilities for the users. We said we're going to look at regret minimizing agents, and next we'll look at our auction setting and see what happens in the dynamics and discuss strategic user behavior in a more general context as well. So the auction formats we're going to look at are second price and first price auctions, and second price auction is well known to be dominant strategy incentive compatible. So here perhaps the naive expectation would be that we will get what's called the second price outcome, where the agent with the higher value should always win and pay the second price, an amount of payment equal to the second highest value. First price auctions are known to be not incentive compatible. The equilibria do give the second price outcome, but on the other hand, they have coarse equilibria that lead to different outcomes. So here, it's less clear what we could expect. And the questions we ask are first, what's going to happen when we let learning agents play in these auctions? So this is a question about learning dynamics. And second, what should the users do? And in particular, is it in the best interest of a user to truthfully report his objective function, his value, to his own bidding agent? And like I mentioned, to answer these questions, we will need to look deeper into the dynamics between those bidding agents and understand what is the meta game, the meta auction that these users actually play. And we will see that the first point here gets a negative answer. We're not going to get the second price outcome in the second price auction when it is played through these bidding agents, whereas in the first price auction, we are going to get the second price outcome. Let's see how this looks like. So what we have in this result here is that if we have two multiplicative weights agents playing the second price auction, then they're going to converge to a distribution in which the high agent always wins, but he pays strictly less than the second price. So we don't get the second price outcome here. And we can also see this in simulations. So on the left here, we see the bids over time. We see that the high agent always wins, except for a small number of times in the beginning. And we also see that the average bid of the low agent is significantly below the second price, which is 1/2 here. And this 0.27 is in fact going to be the average payment that the high agent is going to pay. So he pays significantly less than the second price. On the right, we just see the empirical bid densities from these simulations. So this is a result about learning dynamics. What does this mean for our users? So from their perspective, the second price auction, when it is played through these multiplicative weights agents, is no longer incentive compatible. And this is very much in contrast to our basic intuition on second price auctions, that when they are played directly, they are incentive compatible. And now, when we look at first price auctions, so here we see that if we have two mean-based regret minimizing agents, mean-based learning algorithms is a large class of algorithms defined in the paper cited here. So if their dynamics converge to some distribution, then this distribution, the high agent always wins, and he pays the second price. And again, we can see this also in simulations. We see that the high agent always wins, and the bids converge to the second price. Now, what does this mean for users? So from their perspective, a user enters some number into the auto bidding agent interface, and in the long term, he observes the second price outcome. So overall, what he sees looks like a second price auction. So the first price auction with mean-based regret minimizing agents is incentive compatible. And again, this is in contrast to our basic intuition on first price auctions, which are not incentive compatible when they are played directly, and also in contrast to our result on second price auctions. And now let's turn to look at the more general context of general games, not just in auctions. So in this paper, we define this metagame model for general game settings. So now the underlying game doesn't have to be an auction, it can be any game. And the users enter some parameters that are related to the objective function that their learning agents are going to optimize. And in this paper, we also analyze several classes of games, and we see a broad range of phenomena that arise depending on the structure of the underlying game. For example, in dominant solvable games, we see that players that have a dominant strategy in the game still prefer to misreport their parameters, their utilities to their own learning agents. And in equilibria of the meta game, of the game in which every player decides what parameters to report to its agent, we see that we get cooperative outcomes. we get win-win situations. In Chrono competition games, again, we see that players prefer to misreport their private parameters, their preferences, to their learning algorithms. And we see two types of equilibria that can arise depending on the structure of the underlying game. In one type of equilibria, all the players try to manipulate their own agents, but eventually everyone loses from this. So this is similar to a prisoner's dilemma. And in a different type of equilibria, one player actually manages to drive the opponent out of the market and increase his own gains. And in opposing interest games, those are games similar to matching pennies, we see that players have incentives to manipulate their own agents. So using the true parameters is not an equilibrium of the metagame, but we see that in equilibrium of the metagame, everyone is misreporting their parameters, but eventually they get the same outcomes as in the case where they use the true parameters. So we see this broad range of phenomena that can arise where we get cooperative outcomes, or everyone loses, or one player gains and the other loses, or everyone is trying to manipulate, but eventually nothing changes. And generally, we see that users have incentives to misreport their private parameters to their own learning algorithms. And we see that these kinds of strategic manipulations by the users can lead to significant implications on game outcomes. And I think a takeaway is that we need to consider these points where we analyze or design strategic systems that include automated agents, because the actual game that the users are going to play might be quite different. Let me very briefly conclude. We talked about metagames between users of learning agents. We saw that learning dynamics induce incentives for the users and induce metagames between them. And metagames can sometimes be very different from the original underlying game. And in auctions, we saw that second price auctions may lose their incentive compatibility, whereas first price auctions become incentive compatible, at least for a large class of regret minimizing agents. So this is a very quite broad space to explore, and there are many interesting directions to continue with, and interesting follow-up work and parallel work that has been done. And I'll be very happy to discuss any ideas, or please feel free to write me an email about any questions that you have around these topics. With that, thank you. Thank you very much, everyone.